Hi everyone. Thank you for the introduction. You know, when Umesh invited me to attend this event, I got really excited. I saw all the speaker list, and I thought, great, I'll go and I'll talk about something. And then I ran into a problem, which is that a lot of the technical work that we're doing at OpenAI I actually can't talk about. So I was really racking my head, what could I talk about? Right now, so as of not too long ago, I switched all my focus to working on AI alignment, all my research focus, and we'll have very cool results to show there, but not just yet. So I'm like, okay, so this would have to be for the next talk, but what would be good for this talk? And I came up with something. I'll tell you about some very old results that we had at OpenAI many years ago, back in 2016 even, which really affected the way I think about unsupervised learning. And I thought I'd share them with you. It is possible that at this point you'll all find them obvious, but maybe not all of them. So there is at least a small chance that you'll find it interesting. So I want to set the expectations modestly and then hopefully exceed them. So a theory of unsupervised learning. How can such a thing exist? So, okay. Before we talk about unsupervised learning, we want to talk about learning in general. What is learning and why does learning work at all? Why should learning work at all, and why should computers be able to learn? And now we are just used to the fact, we take it for granted that neural networks learn, but why do they? Like, mathematically, why should they? Why would data have regularity that our machine learning models can capture? So that's not an obvious question. And one important conceptual advance that has taken place in machine learning many years ago by multiple people was the discovery and the formalization of supervised learning. So it goes under the name of pack learning or statistical learning theory. And the nice thing about supervised learning is that it gives you a precise mathematical condition under which learning must succeed. You're told that if you have some data from some data distribution, that if you manage to achieve a low training loss and the number of your degrees of freedom is smaller than your training set, then you will achieve low test error, and you are guaranteed to do so. So you have a mathematical condition where you can say, well, if I did find a function out of my function class which achieves low training error, then learning will succeed. And you can say, yeah, this is a very sensible mathematical thing that we can reason about. And that's why supervised learning is easy. And then you had all these theorems, which I thought were simple. I found them elegant. You've seen maybe theorems like this. If you have basically it's like, this is the sort of thing where if you know it, you're going to say, oh yeah, that thing. And if you don't know it, it will not be possible to explain it in 30 seconds. Though it is possible to explain it in 5 minutes, just not 30 seconds. None of this stuff is complicated. And you've got your little proof, which says, well, if you have some number of functions in your function class, the probability that your train error will be far from your test error for at least one function, there is some math. And the math is simple. This is all the math, 3 lines of math. So 3 lines of math can prove all of supervised learning. Well, that's nice. That's very nice. So supervised learning is something that is well understood. Comparatively speaking, well understood. We know why it must succeed. So we can go forth and collect large supervised learning data sets and be completely certain that models will keep getting better. So that's the story there. And yeah, I forgot to mention a very important piece of this result. The test distribution and the training distribution need to be the same. If they're the same, then your theory of supervised learning kicks in and works and will be successful. So conceptually, it is trivial. We have an answer for why supervised learning works, why speech recognition should work, why image categorization should work, because they all reduce to supervised learning, which works, which has this mathematical guarantee. So this is very nice. Here, I want to make a small side comment on VC dimension to those of you who care about such things. There may be a small subset, so if you want to zone out for the next 30 seconds, feel free to do so. So a lot of writings about statistical learning theory emphasize the VC dimension as a key component. But the main reason the VC dimension, in fact, the only reason the VC dimension was invented was to allow us to handle parameters which have infinite precision. The VC dimension was invented to handle precision, like parameters with infinite precision. So if you have your linear classifier, every parameter has infinite precision. But then, of course, in reality, all our floats are finite precision, and their precision is shrinking. So you can, and you could, so you have your, so the number of functions that are implemented by a computer is actually small, and you can reduce it back to the little, this little formula, which gives you pretty much all the best bounds that you can get from supervised learning. So I find this to be cool. I find this to be appealing because you have fewer lines of proof. Okay, now let's talk about unsupervised learning. So I claim, first of all, what is unsupervised learning? What is it? Supervised learning is like, yeah, you've got your data that says, here, do this, here, do that, and you have all this data. You do well in your training error is low. You have more training data than degrees of freedom in your function class, parameters, but maybe other things too. Degrees of freedom, like bits. And you say, okay, your supervised learning will succeed. But what is unsupervised learning? What can you say at all about unsupervised learning? And I'll say that at least I have not seen like an exposition of unsupervised learning which I found satisfying. How to reason about it mathematically. We can reason about it intuitively, but can we reason about it mathematically? And for some context, what is the old dream of unsupervised learning? Which, by the way, this dream has been fulfilled, but it's fulfilled empirically. Like, can we go just a tiny bit beyond the empirical results? Like the idea that you just look at the images or you just look at the text without being told what to do with them, and somehow you still discover the true hidden structure that exists in the data, and somehow it helps you. But why? Why should it happen? Should it happen? Should we expect it to happen? You don't have anything remotely similar to the supervised learning guarantee. The supervised learning guarantee says, yeah, like, get your low training error and you're going to get your learning. It's going to be great success. Unsupervised learning, it appears that it's not this way. And like people were talking about it for a long time. In the 80s, the Boltzmann machine was already talking about unsupervised learning. And unsupervised learning also did not work at small scale. But the old ideas were there, like the noisy autoencoder. To those of you who remember it, it's like BERT or the diffusion model. Like within it, it's a tiny twist, the tiniest of twists. The language models of all times, they also, generated cool samples for their time, but their unsupervised learning performance was not as impressive as those of today. But I want to make the case that it is confusing, because it's like, why is it confusing? You optimize, like, how does unsupervised learning work? You say, okay, let's optimize some kind of reconstruction error, or let's optimize some kind of denoising error, or like some kind of self-supervised learning error. You optimize one objective, right? Oh yes, I just said that. But you care about a different objective. So then, doesn't it mean that you have no reason to expect that you'll get any kind of good unsupervised learning results? Or rather, you do get them empirically, but like, is it going to be, like, the level of mystery is quite high, I claim. Like it seems like a totally inaccessible phenomenon. You optimize one objective, but you care about another objective. And yet it helps. How can that be? Magic. Okay. So yeah. The other thing, by the way, is that well, I guess I'm gonna say something which is only 90% true. Unsupervised learning doesn't. You could say, okay, so you just learned the structure in the input distribution and it helped you. But then, what if you're training from the uniform distribution? Then all your unsupervised learning algorithms will fail. How should you think about that? So what can we say? Do we need to make assumptions? What kind of assumptions? So I'd like to present potentially a way of thinking about unsupervised learning, which I personally find it interesting. Perhaps you'll find it interesting too. Let's find out. So I want to show you one way of doing unsupervised learning, which is not necessarily widely known because it never became the dominant way of doing unsupervised learning. But it has the cool feature that, similarly to supervised learning, it has to work. So what kind of mysterious unsupervised learning procedure, where you're not given any labels to any of your inputs, is still guaranteed to work? Distribution matching. Distribution matching. So what is distribution matching? Say I've got my data. I've got X and I've got Y. My data sources. There's no correspondence between them. Just got two data sources. Data source X and data source Y. Data source Y. Language 1, language 2. Text, speech. No correspondence between them. Let us look at this criterion. Find the function f such that the distribution of f of x is similar to the distribution of y. It is a constraint on f. And in the case of machine translation and speech recognition, for example, this constraint might be meaningful. Like you could say, yeah, if I have like long sentences, if you tell me that you have a function such that the distribution, you take your distribution of English sentences, you apply the function f to them, and you get something which is very similar to the distribution of French sentences, you can say, okay, I found the true constraint about f. If the dimensionality of x and the dimensionality of y is high enough, that's going to give you a lot of constraints. In fact, you might be able to almost fully recover f from that information. This is an example of supervised learning, of unsupervised learning, where it is still guaranteed to work in the same sense that supervised learning is guaranteed to work. Also, substitution ciphers, like little simple encryptions, will also fit into this framework. So that's the thing, like, okay. And so like, I ran into this. I've independently discovered this in 2015. And I got really fascinated by it because I thought, wow, maybe there is something meaningful, mathematically meaningful, that we can say about unsupervised learning. And so, but let's see, the thing about this setup is that still it's a little bit artificial. It's still, real machine learning setups aren't like this. And the way we like to think about unsupervised learning isn't that also. Okay, now I'll present to you the meat of what I wanted to say. How a proposed way to think about unsupervised learning that puts it on par with supervised learning. It says, okay, what is it doing mathematically? How can you be sure that your unsupervised learning is good? Compression to the rescue. Obviously, it is well known, I shouldn't say obviously, it is not obvious, but it is well known that compression is prediction. Every compressor can be turned to a predictor and vice versa. There is a one-to-one correspondence between all compressors and all predictors. However, I would argue that for the purpose of thinking about unsupervised learning, the language of compression offers some advantages. At least for me it did. Perhaps it will for you too. So consider the following thought experiment. This thought experiment is the most important slide. Say you have two data sets, X and Y. You have two data sets, two files on your big giant hard disk. And say you have a really great compression algorithm, C, which takes data in and outputs compressed objects out. Say you compress X and Y jointly. You concatenate them. You take the two data sets and you concatenate them and you feed them to your compressor. What will happen? Well, let's see. And in particular, an important question is, what will a sufficiently good compressor will do? My answer is, very intuitively, it will use the patterns that exist inside X to help it compress Y, and vice versa. You could make the same claim about prediction, but somehow it's more intuitive when you say it about compression. I don't know why that is, but I find it to be the case. So that's our clue. And you can make an equation like this, where you say, hey, if your compression is good enough, if it's like a real great compressor, it should say that the compression of your concatenation of your giant files should be no worse than the separate compression of your two files. So any additional compression that was gained by concatenation is some kind of shared structure that your compressor noticed. And the better your compressor is, the more shared structure it will extract. The gap is the shared structure, or the algorithmic mutual information. So that's interesting, right? You can see what I'm alluding to. Y is the data of your supervised task. X is your unsupervised task. But suddenly, you have some kind of mathematical reason for the information, for the patterns in X to try to help Y. Notice also how it generalizes distribution matching. If we are in the distribution matching case, where you've got your X is language 1 and Y is language 2, and you're saying, and you know that there exists some simple function f that transforms one distribution into the other, surely your compressor, if it's good, will notice that and make use of that, and maybe even internally try to recover this function. So I think that's pretty cool. We've closed the circle. So how do we formalize it then? What will be the formalization of unsupervised learning? Let's see if I can do it. Consider an ML algorithm. So here, by the way, in what follows, I'll be a bit sloppy, and I will use compression and prediction interchangeably. Say you have a machine learning algorithm A. It's an algorithm A, and it tries to compress Y. And say it has access to X. X is file number 1, and Y is file number 2. You want your machine learning algorithm, your compressor, to compress Y, and it can probe X as it sees fit. The goal is to compress Y as well as possible. We can ask ourselves, what is our regret of using this particular algorithm? You'll see where I'm getting at. Regret relative to what? If I do a good enough job, if I have, being low regret means that I've gotten all the help that I can possibly get from this unlabeled data. This unlabeled data has helped me as much as possible, and I don't feel bad about it. I don't feel bad. I don't feel like I've left some prediction value on the table that someone else with a better compression algorithm could have used. That's what it means. And in particular, it's you can go and you can sleep happily at night knowing that if there is some information in the unlabeled data that could help my task, no one could have done as good of a job as me. I've done the best job at benefiting from my unlabeled data. So I think that is a step towards thinking about unsupervised learning. You don't know if your unsupervised data set is actually useful It may be super useful. It may have the answer. It may be totally useless. It may be the uniform distribution. But if you have a low regret unsupervised learning algorithm, you can say, whether it's the first case or the second case, I know I've done my best. I know I've done my best at benefiting from my unlabeled data. And no one could have done better than me. Now I want to take a detour to theory land, which is a little obscure. I think it is interesting. Kolmogorov complexity as the ultimate compressor gives us the ultimate low regret algorithm, which is actually not an algorithm because it's not computable. But you'll see what I mean really quickly. So Kolmogorov, first of all, like for some context, who here is familiar with Kolmogorov complexity? Okay, about 50%. Yeah, the Kolmogorov complexity is the kind of thing which is easy to explain in 1 minute. So I'll just do it. It's like, imagine if I give you some data, or you give me some data, and I'm going to compress it by giving you the shortest program that can possibly exist. The shortest program that exists, which if you run it, outputs your data.
There's a typo.
Oh.
X.
Typo.
Okay. Y instead of Y should be X.
Yes, that is correct. You got me. It is the length of the shortest program which outputs X. Yes. Intuitively, you can see that this compressor is quite good because you can prove this theorem, which is also really easy to prove. Or rather, it's easy to feel it. And once you feel it, you could kind of believe me that it's easy to prove. And you can basically say that your Kolmogorov compressor, if you use that to compress your strings, you'll have very low regret about your compression quality. You can prove this result. It says that if you got your string X, your data set, database, whatever, the shortest program which outputs X is shorter than whatever your compressor needed output, and however well your compressor compressed your data, plus a little term which is however many characters of code you need to implement your compressor. Intuitively, you can see how it makes sense. The simulation argument, right? The simulation argument. If you tell me, hey, I've got this really great compressor C, I'm going to say, cool. Does it come with a computer program? Can you give this computer program to K? And K is going to run your compressor because it runs computer programs. You just need to pay for the program length. So without giving you the details, I think I gave you the feel of it. Kolmogorov complexity, the Kolmogorov compressor can simulate other computer programs, simulate other compressors. This is also why it's not computable. It's not computable because it feels very much at liberty to simulate all computer programs. But it is the best compressor that exists. And we were talking about good compression for unsupervised learning. Now let us generalize a Kolmogorov complexity, a Kolmogorov compressor, to be allowed to use side information. Oh, more than detailed. So I'll make this detail. I'll reiterate this point several times because this point is important. Obviously, the Kolmogorov compressor is not computable. It's undecidable. But hey, because it's searches over all programs. But hey, did you know that if you run SGD over the parameters of some neural net with 100 layers, it's automatically doing program search over a computer which has a certain amount of memory, a certain number of steps? It's kind of like micro Kolmogorov, fitting a neural net. You kind of see the feel, the similarity. It's kind of magical, right? Neural networks can simulate little programs. They are little computers. They're circuits. Circuits are computers, computing machines. And SGD searches over the program. And all of deep learning hinges on top of the SGD miracle, that we can actually train these computers with SGD. That works. And actually find those circuits from data. And therefore, we can compute our miniature Kolmogorov compressor. And the simulation argument applies here as well, by the way. I just want to mention this one fact. I don't know if you ever tried to design a better neural network architecture, what you'd find is that it's kind of hard to find a better neural network architecture. You say, well, let's add this connection, let's add that connection, and let's like modify this and that. Why is it hard? The simulation argument, because your new architecture can be pretty straightforwardly simulated by your old architecture. Except when it can't, those are rare cases. And in those rare cases, you have a big improvement, such as when you switch from the little RNN to the transformer. The RNN has a bottleneck, the hidden state. So it has a hard time implementing the transformer. However, had we found a way to engineer an RNN with a very, very large hidden state, perhaps it would become as good as a transformer again. So this is the link. You start to see how we switch from the formal land to neural network land, but you see the similarity. So conditional Kolmogorov complexity as the solution to unsupervised learning. You can basically have a similar theorem where I'm not going to define what, well, I'm going to define what k of y given x is. It's like the shortest program which outputs y if it's allowed to probe x. That's the length of that shortest program which outputs y if it allows to probe x. And you can prove the same result. And you can see immediately that, yeah, this is definitionally the solution to unsupervised learning. If you use that, you can sleep very, very safely at night, soundly at night, knowing that no one does unsupervised learning better than you, right? It's literally that. So this is the ultimate low-regret solution to unsupervised learning, except that it's not computable. But I do think it's a useful framework. And here we condition on a data set, not an example. And this thing will extract all the value out of x for predicting y. The data set, not the example. So this is the solution to unsupervised learning. Done. Success. And there is one little technicality which I need to spend a little bit of time talking about, which is, we were talking about this conditional Kolmogorov complexity, right? Where you are talking about compressors that get to try to compress one thing while having access to another thing. And this is a bit unnatural in a machine learning context when you care about like fitting big data sets. At least as of today, although it's changing fairly rapidly, but I think it's still fair to say that there is no truly good way of conditioning on a big data set. You can fit a big data set, but you can't condition on it, not yet, not truly. So this result says that, hey, if you care about making predictions about your supervised task y, using the good old-fashioned Kolmogorov compressor, which just compresses the concatenation of x and y, is going to be just as good as using your conditional compressor. There are more details and a few subtleties to what I just said, and I'm happy to talk about them offline in the event someone is interested in them. But that basically says that if before you're saying, hey, the previous slide said that you can use this conditional Kolmogorov compressor to solve unsupervised learning, this says that you can also use your regular Kolmogorov compressor. Just throw all your data, take all your files, concatenate them, compress them, and that's going to make some great predictions on your supervised task, the task that you care about. There are some intuitions about why this is true. This result is actually like, proving this is slightly more tricky, so I won't do it. And yeah, so the solution to unsupervised learning, just give it all to your Kolmogorov complexity, to your Kolmogorov compressor. Okay. And the final thing is, I'll mention that this kind of joint compression is maximum likelihood if you don't overfit. If you have a data set, then the sum of the likelihood given your parameters is the cost of compressing the data set. You also need to pay the cost of compressing the parameters. But you can kind of see if you now want to compress two data sets, no problem. Just add more points to your training set, to your data set, and add the terms to the sum. So this concatenation, this joint compression is very natural in a machine learning context, which is why it was worth the hassle of saying, yeah, like we have our conditional Kolmogorov complexity, and then I made some argument, I made some claim without fully defending it, but it is possible to defend it. that using regular, just compress everything Kolmogorov complexity works also. And so I think this is elegant. I like it. Because then it says, well, okay, if you squint hard enough, you can say that this explains what our neural network's doing. You can say, hey, SGD over big neural networks is our big program search. Bigger neural networks approximate the Kolmogorov compressor more and more and better and better. And so maybe this is also why we like big neural nets, because we approach the unapproachable idea of the Kolmogorov compressor, which truly has no regret, and we just want to have less and less regret as we train larger and larger, as we train larger and larger neural nets, as far as extracting predictive value is concerned. Now, the way this applies to the GPT models, I claim that it applies to the GPT models also, this theory. But the thing that's a little bit tricky with the GPT models is that the theory of their behavior can also be explained without making any references to compression or unsupervised learning. You just say, no, it's just the conditional distribution of text on the internet. Few-shot learning, just imagine a document with some repeated patterns. The pattern is probably going to continue. So the GPT models can intuitively be explained, at least their few-shot behavior can definitely be explained without alluding to this theory. And so I thought it would be nice. Can we find some other direct validation of this theory? Can we find a different domain, like vision? Because vision, you have pixels. Can you show that doing this on pixels will lead to good unsupervised learning? And the answer is yes, you can. This is work we've done in 2020, which is called the iGPT. And it's an expensive proof of concept. It was not meant to be a practical procedure. It meant to be a paper that showed that if you have really good next step predictor, you're going to do great unsupervised learning. And it was proved in the image domain. And there, I'll just spell it out. You have your image. You turn it into a sequence of pixels. Each pixel should be given some discrete value of intensity. And then just do next pixel prediction with the same transformer. That's it. Different from BERT. Just next token prediction, because this maximizes the likelihood, therefore compresses. And like we see, one immediate result we see, these are results on CIFAR10. You have models of different sizes. This is their next step prediction accuracy on their pixel prediction task, on their unsupervised learning task. And this is linear probe accuracy. Linear probe, when you pick some layer inside your neural net, the best layer, fit a linear classifier and see how well it does. You got these nice looking curves and they start to get more and more similar. It's kind of what you want. It's like, it's working. Pixel prediction of the same variety as next word prediction. Not just pixel, not mere pixel prediction, but next pixel prediction. Leads to better. Leads to better and better unsupervised learning. I thought that was pretty cool. And we tried it, we scaled it up to various degrees, and we showed that indeed it learns reasonably well, where we came close, but we didn't like fully match the gap between our unsupervised learning and the best unsupervised learning of the day on ImageNet. But it was clearly it did feel like it scaled, and it was a matter of compute. Because these things use large, high-resolution images, and we use like tiny 64 by 64 images with giant transformers for the day, tiny by today's standards, but giant for the day, 6 billion parameters. So this you do your unsupervised next pixel prediction on a big image data set, and then you fit your linear probe on ImageNet, and you get strong results. Like, okay, that is cool. CIFAR, we got one of the cool things is that we got 99% on CIFAR10 with this. That was cool. 2020 it was a different time, but it was cool. I'll close with a couple of comments on linear representations. The thing, look, I like the compression theory because I feel like it just bothered me for a long time that you couldn't think rigorously about unsupervised learning. I claim now you can, at least to some partial degree, Still lots of waving of hands is needed, but maybe a bit less than before. But it doesn't say why your representations should be linearly separable. It doesn't say why linear probes should happen. But linear representations happen all the time, and the reason for their formation must be deep and profound, and I think we might be able to crisply articulate it at some point. One thing which I thought was interesting is that these next pixel prediction models, autoregressive models, seem to have better linear representations than BERT. And like the blue accuracy is BERT versus autoregressive. I'm not sure why that is. Or rather, I can speculate, have some speculations, but it would be nice to, I think it would be nice to gain more understanding for why, like really why those linear representations are formed. And yeah, this is the end. Thank you for your attention.
Could you provide the speculation?
Yeah, oh yeah. I think the speculation is basically that if you're doing next pixel prediction, you're predicting the next pixel from all the previous pixels. So you need to look at the long range structure. But in BERT, you have your vector, and let's say you drop 25% of the tokens, of the pixels in this case. Then any prediction that you have can actually be done quite well by looking a little bit into the past and a little bit into the future. So you remove all the hard prediction tasks, or you make them much easier. The hardest prediction task in the next pixel prediction is a lot harder than the hardest prediction task in the BERT prediction case. So this is an argument. We maybe even be able to test it if we think a little, if we try to design an experiment to test it. But yeah, that's a speculation.
Is there a more robust 2D version of next pixel prediction?
I would say more robust. I would say anything you do at all that turns a neural network into a probabilistic model that assigns probabilities to different inputs is that. So the other big way of doing next token prediction is diffusion models. Diffusion models also, like not the ones that are, so the diffusion models that people use in like high quality image generators don't really maximize the likelihood of their inputs. They have a different objective, but the most original formulation is maximizing likelihood. And by the way, the diffusion model is a counter argument the diffusion model also, I would claim, should have worse representations than a next token prediction model for the same reason that BERT doesn't. So I feel, this further, in my mind, increases the mystery of what leads to linear representations to form.
Yeah, thanks for the talk. I like the analogy between Kolmogorov complexity and neural networks. I guess one kind of place where it seems like there's a disanalogy is that neural networks have training dynamics, and if you do something like just take all the computer programs, it's more memoryless, right? So if we're compressing with Kolmogorov complexity, like the order of the data doesn't matter. It clearly does for neural nets. You have like simple heuristics and features that are learned early in training that probably stick around late in training. And so I guess you have thoughts on how to think about that in the context of this picture.
Yeah, I mean, the analogy isn't perfect, that is true. And the way in which you describe it's imperfect. Like, the place where the analogy breaks down the most is in the search procedure, right? This is really what you're alluding to, like, hey, like order of data matters. Why? Because we are using a weak search procedure. Kolmogorov compressor uses the infinitely expensive search procedure of just enumerate everything from scratch each time. So yeah, I mean, I would say that caution should be used with this particular analogy. It's very clearly not universally applicable, But I do think that I do think that there is some value here in explaining where unsupervised learning comes from.
So your formal going back and forth between compression and next bit prediction, you were connecting that to relating unsupervised learning to supervised learning. So if you sort of backtrack from cryptography, there's sort of a theory goes back to the 80s where they talk about compression being equivalent to next bit prediction, being equivalent to being able to distinguish into distribution. So if you have an algorithm that can distinguish, then you have an algorithm that can predict, then you have an algorithm that can compress. I mean, cryptography is the other way, right? You say there is no way to compress things uncompress, and therefore there is no way to distinguish, and there is no way to distinguish. So I wonder if this idea of being able to distinguish, how could that would that translate to anything natural?
So I think I understand. I think I understand the question. I think let me paraphrase. So I'm not super well versed in the area that you mentioned, but you're saying if you can distinguish to distribution, you can use that distinguishability to make to predict. And I guess the question would be, what's the like? I have some.
You have samples from one, you have samples from the other, and you can tell them apart.
And so I guess my question is, how well can you predict? Well, you're talking about you can predict a little bit. Is that what you're alluding to?
You can predict what the next bit would be, let's say, in a sample.
So yeah.
What you can predict.
I mean, I can mention one thing that is related, which is energy-based models. So energy-based models offer yet another way of turning neural networks into probability distributions, where an energy-based model will say, I just give me your configuration of vectors, and I'm just going to tell you how it feels, and then you normalize over all of them. And I feel like when it comes to energy-based models, in particular, ratios of distributions correspond to differences of energy. Maybe there is some relation to what you're saying. I think I'm probably not like precisely commenting on the thing that you said, but I don't think I have anything more to add, unfortunately.
Ilya, maybe I'll just put in a tiny word to defend the honor of VC dimension.
Go ahead.
Well, so, I mean, in 2007, I had this theorem about pack learning of quantum states, right? And this was precisely an example where even if you don't care about infinite precision, even if you discretize the state space, like you look at the VC dimension or the fat chattering dimension or whatever, and it is exponentially smaller than the log of the size of the hypothesis class. So I do think there are cases where you still want VC dimension.
That is a cool example.
So I didn't completely follow your notation. Capital X was a sample from a distribution.
No.
The distribution is
The data set.
So then the transformer SGD, I'm not sure if you can think of it as the best program for compressing the distribution. Maybe because it's only given one sample at a time.
That's true. There is one other assumption that we are making. So if you look at the total training loss, say you have some neural network, doesn't need to be a transformer, some neural network which assigns log probabilities to your data, and you have some large number of training cases. You can run the neural network, and you have some neural network. You can compute its log probability on each case, and you can take their sum. And that's going to be the log probability that the neural network assigns to the entire data set. Now, the neural network is this particular formulation makes the neural network unable to explicitly notice, like maybe temporal, any kind of structure in the order of the data. But I still claim it's meaningful to say that, yeah, like, okay, you can compute the entire log probability of the data set, and that gives you your negative log probability, literally the number of bits you need to compress this data set relative to using this neural network as a compressor.
Yeah, if I
Paraphrase, I think you're arguing for compression as a framework for understanding or motivating unsupervised learning. And a point you made at the end was that if you apply that framework to language models, to next word prediction, it can feel a little maybe superficial because next word prediction, any text task can be converted to next word prediction. And so unsupervised learning is kind of superficially the same as supervised learning for text. So then we turn to image GPT, where you can't formulate any image task as next pixel prediction. Maybe you could, but let's just say you can't. But then you can use the linear representation as a way of showing that compression is a good way to formulate unsupervised learning. But then there are highly effective compressors that wouldn't give you a useful linear representation. So I'm wondering, are there any cases where unsupervised learning and supervised learning are not superficially the same, like in text, but that you don't require your compressor to give you an effective linear representation to show that compression is a good unsupervised objective?
Yes. So that's a very I have thoughts on this question. So first of all, I will say that the linear representation, good linear representation, is a bonus. At no point does this argument say, and therefore linear representations should emerge. However, I would argue that the theory does say that good fine-tuning should emerge, because joint compression is kind of like hacky approximate fine-tuning using the bad search algorithm, which is SGD. Now we know that the evidence from these old experiments suggests that BERT learns worse linear representations than next pixel prediction when run on images. And perhaps the same is true for diffusion models. That seems highly likely. I think it'll be very interesting to see how the fine-tuning of diffusion models compare. Maybe someone knows already here.
I wonder if you can take your ideas for unsupervised learning and bring them back. It seems to me that there could be some insights you could take back to supervised learning, which back learning doesn't cover.
Well, I think here this gives you more like insight into the particular insight that you might get here is insight into the function class, the desired function class. Like you want your neural net to have many layers, for example, right? If you have many layers, it can do more thinking. You want those layers to be wider, bigger, bigger neural nets. I mean, essentially, this is like what the field has already discovered.
But you might not need more examples than number of parameters. In supervised learning, this might give you an explanation for why you don't need necessarily more parameters.
Like that's right. So this might, for example, be like, so there is the weakness of this theory, by the way, this theory has a huge practical weakness, which is it ignores compute cost. It only focuses on information. So like, you're all familiar with the universal transformer. Maybe it's like, basically it's a transformer, we use the same weights at each layer. It's a great idea, except that if you want to have a lot of parameters, you need to pay for it a lot with compute. Nobody wants to do that. You don't ignore compute cost. This ignores compute cost. If you ignore compute cost, it gives you a recipe of how to proceed.
What do you think the importance is of the autoregressive modeling in particular of the probability distribution? Like, you can view BERT as sort of kind of doing maximum likelihood training, right? I think you can find ways to sample out of BERT, for example.
So certainly diffusion models can be set up to be maximum likelihood models. And so all this theory predicts that diffusion models should also be, it should be possible to make diffusion models to do equally great things, perhaps with some constant factors of, because this is like, as the earlier answer, this is not a compute sensitive theory. So it's going to say, okay, like maybe you need like a factor of 10 or 15 compute, and then things will be the same between the autoregressive and diffusion model. The autoregressive model it's just simple, it's convenient. Maybe the energy-based model will do even greater things, but from that perspective, they're all the same.
It seems like GPT-4 may be the best compressor at the moment, which presumably is the largest model out there as well. So on one hand, it's able to compress better. On the other hand, the size of the compressor itself is increasing. Or is it that it's actually not necessarily the case from the perspective of the theory, Kolmogorov complexity?
Well, I mean, what matters is that the cost of the, like, what you really want is for the, like, there is another place in way in which this theory doesn't quite correspond to reality, because this theory says, okay, you have a fixed data set, you want to compress it. But in the way we train the GPT models, you say, okay, you have this big training set, and then you have like a test set, which is assumed to be infinite. If the test set is infinite and you care about compressing the test set, then you don't care about the size of your compressor, so long as this test set size is much larger. So I would say that this is also like a disanalogy where some more careful thinking could be useful to get clarity.
Is it enough to use a validation set that's independent as long as it's separate? That kind of closes the gap.
Is it enough? It's a good thing. It's a good thing to do. Is it truly, like, the thing is, I think it's also, well, actually, like in the single epoch case, right? If you are in the single epoch case, then you can just, like, compute your log probes as you train, and that will be something like the model's compression of the data set. And that gives you also a good estimate of the validation set. So in the single epoch case, I think things are quite similar.
Just wanted to make you aware that there was a paper last month in Findings of SEM. They have used GZIP followed by a k-nearest neighbor classifier for just text classification. So no training, no parameters. GZIP compress strings, just like you should concatenate two strings together, compress them individually, and then compute distance. So there is a way using the output of GZIP as the Kolmogorov compressor.
Yeah. My only comment on that is that gzip is not a very strong compressor of text. So I think, like, it does show that things are possible to some degree, but like all the really meaty stuff happens when you like squeeze the last bits, if you see what I mean.
It seems like it works like a toy proof of concept, but it does work.
I think there was some bug there before this, so
No, it doesn't work.
watch us put that result for now.
Since Jacob brought up curriculum effects and how they appear for neural nets, but not for you don't see it with Kolmogorov complexity. We were just talking at lunch about like what is the current empirical situation about like how much do curriculum effects actually matter, and none of us knew the answer.
Well, it's like, so it's a bit, I have a take on this, which is the easier. So we've done a lot of work as a field to make the transformer, like the architectures that we are using, to be relatively easy to optimize. We found good initializations, we found good hyperparameters. We made changes to the architecture so that training is as easy as possible. The easier is, the more easy the training optimization problem is, the less susceptible you are to curriculum effects. And like it's known, like for example, people who were training all kinds of exotic architectures, like neural Turing machines, for example, which are like these really complicated things, and it's super huge numbers of heterogeneous layers which are different. And that thing, you need to be very, very careful with your curriculum. Because if you give it the full data set right away, it'll just fail.
Right. Let's thank Ilya again.